All right, everybody, welcome back. We're going to talk today about a very important topic, line integrals. Now, I'll say there are multiple types of line integrals that we're going to meet today. So in this first video, I'm just going to describe one of those. That's probably the one that we'll end up using the least. But it's the one that kind of is maybe the most general one that everything else can be explained in terms of. So let's let f be a scalar valued function of 3 variables. So it's a function on space. And let's let c be a curve in space. And I'd like to note off to the side that we could do all of this in the plane, let f be some function of just x and y, and let c just be some curve in the plane. But I'm going to try to do it in space because I think that's going to be where it pops up most when we continue on for the rest of the semester. So we'll parameterize our curve by this formula r of t, which is x of t in the first component, y of t in the second component, and z of t in the third. And let's say that it's some finite length curve, so that t just goes from a to b, and so it's cut off. So now we can evaluate our function, little f, along this curve. And if we evaluate f along r of t, then this gives us a scalar valued function of just one variable t. Okay, so this is like a one variable function from, say, calculus 1. And so we can define some kind of natural ways to take an integral of that function that work similar to the way that we defined integral in calculus 1. So we're going to define 4 different ways to do this. Okay, well, really, the other 3 kind of all go together. So the first one is this that I'm just going to talk about in this video now is the one called integrating f along c with respect to arc length. So let's break our curve as it sits in space. Let's break it into n pieces and say that each one of those pieces has its own arc length, which we'll denote by delta s sub I, where I goes from, say, 1 to n. Okay, then those little pieces are going to be like the bases of rectangles. And as we evaluate our function along that curve, we'll get the sort of height of some rectangles whose areas we're all going to add up. So pick your favorite point in each one of these pieces, say r of ti star. So ti star would be like your preferred parameter, and you evaluate your curve there so you find whatever point in space is sitting along that curve there. And you'll evaluate f at that point. This will give you this proverbial height of a rectangle. Okay? So then this product, f of your preferred point in each piece, times the arc length of that piece, can be interpreted as the area of a rectangle whose base has length, the arc length of that piece of that curve there, and whose height is the function value evaluated at your preferred point in that little piece. And so then the sum of all of these little areas that you've accrued here is a Riemann sum. And we know from all our time being students in the calculus that a limit of a Riemann sum as n goes to infinity, that is to say, as each one of those little pieces gets infinitely small, is going to give us an integral. And the integral that we get in this case is what's called the line integral of f along c with respect to arc length. And it's written in this funny way here. It's written the integral with c as the sort of bound underneath of f of x, y, z, and then they write this notation here, ds. And what it is the limit of that Riemann sum as n goes to infinity. Now you and I know that it's not very likely that we're going to compute an integral this way. So maybe we'll say a little bit more about what's going on with this, and in particular, what is this ds thing here? So that expression ds stands for the differential of the arc length function, which I think you guys might recall from chapter 13. This function, s of t, is the integral from a to t of the length of the tangent vectors of r. So what is this saying here? Each one of these integrals itself, the length from a to t of r of u, right? So s of t is a function whose outputs are lengths of the curve r when you start at a and end at the fixed parameter t that you want. Okay, and the most important thing to remember about this arc length function that we met in chapter 13 was that its derivative with respect to t, if you just use the fundamental theorem of calculus, is just the length of r prime of t. And if you recall what the length of r prime of t is more concretely, if r of t is given by three component functions x of t, y of t, and z of t, then its length of this vector is just the square root of the sum of the squares of the derivatives of each one of the components. So we can, kind of just do abuse of notation there and just bring dt on over here and write that ds, that piece up here in this integral, can be written as the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. Okay, so we get this following formula for the line integral of f along c with respect to arc length. We can integrate from the endpoint parameters a and b of f of x of t, y of t, z of t. This is just f of r of t if you're, wanting to be kind of shorthand about it, times the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. This one you could write as just the length of r prime of t if you're trying to be short. And we'll integrate this expression with respect to t from a to b. So as just one example here, let's let c be the arc of that helix curve, that one that was parametrized by cosine of t in the first component, sine of t in the second component, and t in the last component. And let's look at the arc that goes from t is 0 to pi over 2. And along that curve, let's just pick some random function like f of xyz equals to x squared y. Let's see what's going on there. So then, if we want to integrate f along c with respect to arc length, then we'll form the integral from 0 to pi over 2 of cosine squared t times sine of t. That is this x squared times y, right? We just take x is cosine of t, we square that, and y is sine of t, we stick that there. And then we can't forget to put this length of r prime of t next to it. This is the square root of minus sine of t all squared plus cosine of t squared plus 1. Luckily, minus sine of t all squared plus cosine of t squared gives us sine squared t plus cosine squared t, which is 1, so that everything underneath this square root becomes just 2. And so then we have the integral from 0 to pi over 2 of cosine squared t times sine of t times the square root of 2 dt. And this is a u substitution, right? And I kind of didn't show all my work here because at this point I think we're getting pretty solid with u substitution again. So I let u be cosine of t, right? So then, so then if you let u be cosine of t, then du is negative sine of t dt. And so you'll have that little intermediary problem where your bounds are backwards, but that writes itself by removing the minus sign. So this integral becomes the square root of 2, which can yank outside, times the integral from 0 to 1 of u squared du. And this one's pretty routine, right? That's just 1/3 after you do the integral, so you get the square root of 2 over 3. Now, I will warn you that most instances are not as nice as this helix one, and this square root term can be really kind of a bear. It was nice here because it simplified everything underneath it was a constant. But typically it's difficult to integrate things that look like this. Maybe sometimes some nice things can happen and you can do some kind of substitution or maybe integration by parts. I'm not sure. So just be on the lookout for this. But I think it's important to at least talk about line integrals with respect to arc length because I think they're the sort of first most natural one that you'd want to do. And you might see them pop up on WebAssign and not know exactly what it's talking about when it has this ds thing next to it. So that's what it means. So stick around for the next video. We'll learn 3 other ways to do a line integral of a function along a curve. And those three other ways are going to be very nice because they're going to turn into a way for us to actually find what's called the line integral of a vector field along a curve. And so don't miss that because it is actually super important in this course.